Hi there, this is Ligaya from Boost Revision. In the session today, we're going to be focusing on the AS Equilibria section. So we'll go over the details of what dynamic equilibrium is, what homogeneous and heterogeneous reactions are, remind ourselves about Le Chatelier's principle and the factors that affect the position of equilibrium. And then we'll go on to talking about what the equilibrium constant is, which we call Kc, how to write the expression for that constant, and what that constant means in terms of identifying the position of equilibrium based on the value of that constant. So in today's session, we're not going to go into too much detail on how to calculate values for Kc based on values of concentrations of reactants and products. That's going to be gone over in the next session hosted by Dr. Owusu on Sunday. So on Sunday's session, Dr. Owusu will go through the details of how to calculate Kc from initial concentrations, working out moles, working out equilibrium concentrations, and calculating the value of Kc, including the units for that. And he's also going to go over Kp, the gas equilibrium constant. So for today's session, we're focusing just on the AS level stuff. I'll share my screen with you now so that you can see what we're talking about. I'll just highlight again, just the OCR specification points that we're going to be going through today. Okay, so hopefully you can see my screen now. Like I said, this is the section of the OCR specification that we're going to be looking at today. So section 3.2.3 in chemical equilibrium. If for some reason you are on here, but you are not on the OCR board, then don't worry, because this section is actually very, very similar in all of the exam boards. But just because I know the majority of you guys are on OCR, just so you know, this is the section of the specification we're going to be looking at today. So dynamic equilibrium and Le Chatelier's principle, and then the equilibrium constant. So first of all, just a reminder of what dynamic equilibrium actually means. So you'll have heard of, or you'll have come across the reversible reactions in GCSE before. So we'll just do an example of one here. We've got A plus B going to C plus D. Okay, so this is just a general equation for reversible reaction, obviously highlighting this reversible arrow here to show that this reaction can go in both directions. Excuse me. However, although you can have reversible reactions, they don't always necessarily end up in equilibrium. Some of these reactions will go one way and will only go the other way if you add water or change the temperature or change the conditions in some way. So not all reversible reactions can come to a point of dynamic equilibrium. In order for a reaction to reach a dynamic equilibrium, a couple of things need to be the case. And the first thing is that you need to have your reactants and products in a closed system. What that means is that your reactants and products are not able to escape and you're not adding anything new in. So you could think about this as if these were all gases, these are all going to be gases that are reacting in a closed and sealed chamber, and any of the products C or D that are produced are not able to escape. And this allows them to then react with each other to turn back into A and B and do the reverse reaction. So you have to have a closed system in order for a reversible reaction to come to dynamic equilibrium. Secondly, it's key to remember the idea that for something to come to a dynamic equilibrium, both of the reactions are happening at the same time. So both forward and backward reactions are occurring. And the key thing to dynamic equilibrium is that these reactions, the forward and the backward reactions, are occurring at the same rate, okay? So when you have a reversible reaction in a closed system, and they reach a point where both the forward reaction and the backward reactions are happening at the same rate, that's when we can say that we've reached a dynamic equilibrium. The word dynamic means that both of the reactions are still taking place, and the equilibrium part means that both of the reactions are happening at the same rate. The result of seeing these reactions happening at the same time, at the same rate, is that we'll end up with constant concentrations of the reactants and products. Now, I write constant rather than some other kind of word like the same, because once you've reached equilibrium, you won't see the concentrations of the products or the reactants change. They will remain at the same level that they were in once they achieved equilibrium. But that doesn't mean that the concentrations of the products and the reactants are the same as each other. And this can be, you can see this quite nicely in a simple graph, where, for example, this purple line might be the concentration of the reactants. So we start with a higher level of reactants. As the reaction progresses, the reactants reduce in concentration because they're being used up. And then as the reaction progresses, at some point, it reaches a point of equilibrium where the concentration then remains constant. At the same time, you're going to have the reaction happening where you're going to have products being created by the reaction. So at the beginning, we don't have any products, but as the reaction progresses, we're going to start increasing the concentration of the products as the reactants are reacting to make the products. And then as we get to the point of equilibrium, the concentrations of the products start to level off and start to remain constant. So again, hopefully this graph can help to clarify in your mind that once we reach equilibrium, which is basically at this point here, the concentrations of the reactants and the concentrations of the products now remain constant. However, they are not necessarily the same. So we have the reactions happening at the same rate and the concentrations are remaining constant. And this is so long as we are in dynamic equilibrium. In a second, we're going to talk about factors that may affect the position of equilibrium, and the position of equilibrium will affect the amount of products compared to the reactants, or the relative concentrations of the products and reactants. So if we were to change a factor later on and equilibrium was to shift towards the right or towards the left, then we might have a change in the concentration of the products and a change in the concentration of the reactants, let's say, depending on which direction the equilibrium is shifted. But usually once we shift the equilibrium, usually we come back to a new equilibrium with new concentrations and pressures. And so this second part of the graph is sort of showing what might happen if you change the concentrations and then we re-establish a second equilibrium. So, oops, I'm not sure where that's just gone. Sorry about that. So yeah, so hopefully this graph can sort of help you to clarify in your minds what the meaning of dynamic equilibrium is and how the concentrations of the products and the reactants kind of relate to each other as the progress of the reaction goes on. Okay, so a quick note now just about what the difference is between a homogeneous and a heterogeneous reaction. You may not have come across these terms before, perhaps you have, but it is a key thing to think about, because moving forward from here, when we talk about Le Chatelier's principle and we talk about the equilibrium constant, it's important that you understand that these things actually only refer to reactions that are homogeneous. So a homogeneous reaction is a reaction in which all of the reactants and products, so all of the species that are in your reaction, are in the same state of matter, i.e. they're all gases or they're all liquids. It's unlikely they'll all be solids, but they could be all solutions, for example. But they need to all be in the same state of matter in order for us to have a homogeneous reaction. And in order for Le Chatelier's principle and KC to actually function the way that we learn about them, is we have to have reactions that are homogeneous. So make sure that's something that you do check. It is possible, we'll talk about Kc later on, it is possible to write Kc equations for heterogeneous reactions, but we have to then ignore any elements or species that are in that different state, such as if there's a solid, we just ignore the fact that that's there when we're talking about the Kc. So it's important to be able to distinguish whether you have a homogeneous or heterogeneous reaction. As you can see in the heterogeneous reaction, that is a reaction in which the reactants and products, or there are species in the reaction that are in different states of matter. So I don't have an example written down here, but if we had, for example, a solid reacting with a solution, making another solution and solid, that would be a heterogeneous reaction. Or again, it's quite common to have gases reacting with solids, and that's perfectly fine to have, obviously, but that's a heterogeneous reaction in which the Chatelier's principle would not necessarily apply, and we would have to adjust the Kc expression that we write later on in order to adapt for the fact that we have these reactants and products in different states. Okay, so now we're just going to talk briefly about Le Chatelier's principle and the factors that affect Le Chatelier's principle. Or the factors that affect the position of equilibrium, which is what Le Chatelier's principle is talking about. So you may remember that Le Chatelier's principle states that in a reaction at equilibrium, if a condition such as concentration, pressure, or temperature is changed, the position of equilibrium will shift to counteract the change. So we talked about the position of equilibrium when we were talking about dynamic equilibrium, but that all depends on, obviously, as we said, a closed system where we aren't changing anything. As soon as we change something like the concentration of reactant or product, or the pressure if we are looking at a reaction with gases, or the temperature, then the position of equilibrium will shift to counteract the change. Usually equilibrium will be re-established after this change happens, and this may or may not, as we'll look at later, affect the value of Kc, our equilibrium constant. So that's just sort of the key theory of Le Chatelier's principle, and I will quickly remind you of how these different factors affect the position of equilibrium based on Le Chatelier's principle. So in order to figure out what the effect of temperature is going to be on any particular reaction, we need to know whether the forward reaction is exothermic or endothermic. The reason that's so important is that if we increase the temperature, then the equilibrium is going to shift in favor of the endothermic reaction. Okay, so this is all relating back to what you'll have learned about in energy. Endothermic reactions will absorb energy from the environment, and then the temperature of the surroundings will go down because we've absorbed energy from the surroundings. In the opposite sense, exothermic reactions will release energy into the surroundings, and that will have the effect of increasing the temperature of surroundings. So there's two ways of really thinking about this. One way is that if we increase the temperature, we're giving the reaction more energy, and that is going to give the endothermic reaction the energy it needs to absorb in order to do that reaction. But in terms of Le Chatelier's principle, if we increase the temperature, we're saying that the equilibrium is going to shift to counteract that change in temperature. So if we increase the temperature, then a reaction is going to happen, or the direction of reaction is going to happen that's going to have a result in reducing that temperature again, counteracting that change. So that's another reason why, going back to this slide, why we want to, why the endothermic reaction will be favored. So an example, so if we increase the temperature, the endothermic reaction is favored. Okay, So this is always true in all reactions. That's why it's important to know, is the forward reaction exothermic or endothermic, because that's going to tell us which direction the equilibrium will shift. So as an example, we often use the Haber process to illustrate this example. I don't have the data booklet with me, but I know that the enthalpy change for this is something around minus 92 kilojoules per mole. Okay, and what that tells us, the enthalpy change of this forward reaction, is that the forward reaction is an exothermic reaction because we've got this minus sign here. So the forward reaction is an exothermic reaction, and that means the backwards reaction is an endothermic reaction. Therefore, in the Haber process, if we increase the temperature, then the endothermic reaction, which is the backward reaction, will be favored. Let's say if we increase the temperature, backward reaction is favored, therefore equilibrium will shift to the left. Will shift to the left-hand side, or we could say shift towards the products. Sometimes a question might ask you how this will affect the yield of a reaction. The yield of a reaction is the amount of products that this reaction makes. So if equilibrium shifts to the left, that's going to reduce the yield, because less of the products are going to be created in this situation. And this becomes important when we talk about industrial conditions and how these factors affect industrial conditions and the optimum conditions to use in industry. So just to finish up this point about what happens if we increase or decrease the temperature, if we decrease the temperature, obviously the opposite will happen. So if we decrease the temperature, the exothermic reaction will be favored. So in this example of the Haber process, if we increase the temperature, I'll write it in orange this time since we've said that that's the exothermic one. So if we decrease the temperature, the forward reaction, which is the exothermic reaction, is favored. Equilibrium will shift to the right, or that's in the direction of the products, and therefore will increase the yield. Okay, so we've used the Haber process as an example, but this can be applied to any reaction as long as the first question that we highlighted at the top here is answered. Is the forward reaction exothermic or endothermic? And that is going to be based on the enthalpy change that you'll be given in the question, showing the enthalpy change of the forward reaction. So based on if that's a plus or a minus sign, you decide, is that exothermic or endothermic? Then that will tell you how temperature will affect the equilibrium position of this reaction. Okay. The other two factors you need to know about how they affect position of equilibrium via Le Chatelier's principle is pressure or concentration. And we've written pressure or concentration here because they have the same effect using the same explanation, but obviously with pressure, that's when we've got reactions, reactions in gas state. So it's a homogeneous reaction where everything is a gas. And with concentration, this is when we have solutions or aqueous reactants and products that are in aqueous solution. So I've said that they affect things in the same way, and they kind of do, but the explanation is slightly different. So we'll start first of all with concentration. We'll just go back to the A plus B goes to C plus D situation. If we increase the concentration of A, one of the reactants, then Le Chatelier's principle states that the equilibrium will shift to counteract that change. So equilibrium is going to shift in order to decrease the concentration of A, which will be towards the right-hand side so if we increase the concentration of A, then equilibrium will shift towards the right-hand side in order to, that will use up more A and B, and it will produce more C and D. So in terms of Le Chatelier's principle, increasing the concentration of A will shift it to the right because that will have the effect of reducing the concentration of A again. So changing this initially will shift it to the right. It will then reduce A and B and increase C and D. And so again, we could talk about the fact that that will increase the yield in this particular reaction. The same thing is true if we decrease the concentration. It's unlikely that we would decrease the concentration of a reactant, but something that's often done in industry is that we would perhaps remove products as they are produced. And that happens quite commonly in a lot of industrial reactions. So the Haber process is a good example. As the ammonia is produced in the reaction, it's actually removed from the reaction vessel. And this has the effect of shifting the equilibrium towards the right, and therefore making more products. So again, this is a situation in which we're decreasing the concentration of the products, and therefore equilibrium will shift towards the right-hand side again. I'll just copy this actually. So equilibrium will shift to the right. And that will have the effect of increasing the concentration of your products. So again, this will have the effect of increasing the yield. So if you want to increase the yield of your reaction, let's do it correctly. If you want to increase the yield of your reaction, then you can either increase the concentration of some of your reactants or remove the products as they're produced, and both things will have the same effect of increasing the yield. Of course, the opposite will be true in both. If we decrease the concentration of reactants or increase the concentration of products, that will have the effect of shifting the equilibrium to the left-hand side, but that's usually not what we want to do. Okay, for pressure, again, let's do A plus B goes to, we'll just do A plus B goes to C this time. And actually, I'm going to put 2B here, just to make it clear that we are interested in how many moles we've got on either side. In fact, I'll just keep the D here, but now I'll say we've got A plus 2B goes to C plus D. So to decide what's going to happen if you change the pressure of something in the reaction, well, you can only change the pressure of the whole vessel. We need to look at the number of moles of gas on the left-hand side or the right-hand side. So as we said before, we can only really look at the effective pressure when we have a reaction involving just gases. And we want to focus on the moles of gas on the left-hand side or the right-hand side. Okay, so in this particular example, a generic example, on the left-hand side, we have 3 moles of gas. And on the right-hand side, we have 2 moles of gas. So if we increase the pressure in the vessel, we're going to want to shift the equilibrium in the direction that's going to decrease that pressure again. And so the equilibrium shifts in the direction of the fewer moles. So equilibrium shifts to the right because we have fewer moles of gas on the right. Okay, again, this will increase the yield in this reaction. But obviously this is just one example. It's quite possible and quite common to have an example where perhaps you have 2 moles on the left and 4 moles on the right. Therefore, if we increase the pressure, the backwards reaction is going to be favoured, and therefore equilibrium will shift to the left-hand side in order to decrease the overall pressure in the vessel. Another way you can think about this as well, especially if you find Le Chatelier's principle a bit confusing, especially initially, think about moles of gas as the number of particles we have in the container. So if we start, let's say, with 5 moles of gas overall, but then we increase the pressure, we're going to push all of those particles of gas much closer together. And that's going to have a greater effect on A and B in this case, because there are 3 moles of them, so there are more of those A and B particles, and we'll end up with having more collisions of those A and B particles compared to those C and D particles. If we have more collisions of A and B particles, we're going to create more of C and D. So increasing the pressure is pushing the particles closer together, and that's going to have more of an effect on the side that has the more moles, and that's going to push the equilibrium in the direction of the side that has the fewer moles. So the key thing to remember is that equilibrium always shifts in the direction, oops, that was supposed to be a highlighter. Equilibrium always shifts in the direction of the fewer moles of gas. So with temperature, you need to know, is the forward reaction exothermic or endothermic? An increase in temperature always favors the endothermic direction. For concentration, that's the simplest one. If you increase the concentration of a reactant on the left-hand side, it will shift the equilibrium towards the right-hand side, and vice versa. For pressure, we need to find out how many moles of gas are on the left and the right-hand side of the equation, and equilibrium will shift in the direction of the fewer moles of gas. Just another quick thing to point out here is that if you have the same number of moles of gas on either side, then pressure will not affect the position of equilibrium at all. However, it may affect the rate of reaction, which would still have an overall effect on how you're producing a product in industry, but it will not affect the overall yield or percentage yield of the reaction. So that's just important to know. If there's the same number of moles on either side, pressure will have no effect. Finally, just a quick point about catalyst, because it is in the specification here. So it just says an explanation that catalyst increases the rate of both the forward and reverse reactions in an equilibrium by the same amount, which results in an unchanged position of equilibrium. So catalysts will, as we know, increase the rate of reactions, but in an equilibrium reaction, it increases the rate of both reactions by the same amount. So catalysts will never have an effect on the position of equilibrium. And later when we look at Kc and the expression of Kc, Kc is basically a quantitative way of measuring the position of equilibrium. And so adding a catalyst is never going to have an effect on Kc either. Okay. A quick point about industrial conditions. This is something you will have learned at GCSE, so I'm going to try not to spend too much time on it. But your specification does require you to talk about the importance of of equilibrium to the chemical industry in terms of a compromise between chemical equilibrium and reaction rate. So this is just talking about the compromise between equilibrium, position of equilibrium, which gives us the yield of the reaction, how much of the product we make, compared to the rate, which is how fast we make the product. And other things to consider here as well are safety and economics, i.e. the cost of the reaction. And now the cost is usually due to the amount of energy needed. So for example, if you need to heat up a reaction a lot, then it's going to cost a lot because we have to burn some fuel to produce that energy. Or it could be to do with the cost of, for example, maintaining a high pressure in a pressurized situation. So there could be various things that affect the cost. But whenever you're asked a question about this, That is the effect optimum conditions used in industry. We want to talk about a compromise between yield, which is the amount of products made, rate, how quickly we make those products, as well as safety and economics. So just as an example here with the harbour process, we talked about the fact that it is, again, don't quote me on this value here, but it's an exothermic reaction. The forward reaction is exothermic. The backward reaction therefore is endothermic. And thinking about how this might be affected by pressure, we have 4 moles of gas here, and we have 2 moles of gas here. Okay, so usually when we're talking about the harbour process, as a common example comes up in the exams, we want to talk about what would be the optimum temperature and pressure to use based on these conditions and the Chatellier's principle. So if we want to maximize the yield, that means we want equilibrium to shift to the right. And this would mean we would want to have a very low temperature, because that's going to favour the forward exothermic reaction. And we want to have a high pressure, as high as possible, because that's going to favour the forward reaction as well, because that's got the fewer moles. However, there's a problem, because a very low temperature would cause the reaction to happen very slowly. And in industry, we wouldn't want to have to wait several days or weeks for us to be able to produce enough product to make this economically viable. We're trying to produce some product, in this case ammonia, in order to sell it and use it for something else. So we want to create this at a high enough rate that this makes economic sense. So if we wanted to maximize, sorry, I'll change the color again, to maximize the rate, this goes back to collision theory and kinetics and rates of reaction. We would want a high temperature and also a high pressure. Okay, so in this particular example, but obviously you'd have to look at the question you're given, we will definitely want to use a high pressure, but we need to make a compromise between the yield and the rate to decide what temperature we're going to use. And so usually we use what we would term as a medium temperature, which is actually something around 450 degrees centigrade, which is high enough to make sure the rate is fast, but low enough to not shift the equilibrium too far to the left-hand side. So I'll leave that there for now, but we will, if we have time to go through some exam questions at the end, we will come back to this in some of the exam questions, because this is often asked about, especially in the AS papers, but obviously in any of the papers. So to go on to the equilibrium constant, what it is and how to write the Kc expression. So the equilibrium constant, as I mentioned briefly earlier, is a way of quantifying the position of equilibrium, i.e. calculating a number that will tell you some information about where the position of equilibrium lies, whether it's further towards the right or further towards the left. Of course, as we said, in industry, we're normally trying to get a reaction that's going to be shifted further towards the right. Okay, so this is an example equation, again, A, B, and C. This time for the generic equation, we've used these little A, B, C, and D here to represent the number of moles you would have for each one. So earlier we weren't really too bothered about that, but now for the Kc expression, it is important to know how many moles of each of these we have. So first of all, I'll just highlight what I've written down here. The Kc expression is, in simple terms, a ratio of the concentration of the products to the concentration of reactants in the equation. So ultimately, and we'll talk about this on the next slide as well, if the concentration of all the products was the same as the concentration of all the reactants, you may be able to see that would actually give you a Kc of 1. And that would mean that our position of equilibrium is exactly in the middle because we have the same exact amount of concentration of products and reactants. But of course, that's rarely the case. And so we need to actually calculate what is the exact ratio of products to reactants, and that will give us an indication of where the position of equilibrium lies. So the Kc expression always depends on the chemical equation, and because we're looking at the concentration of the products, which is obviously this side here, we use square brackets to denote concentration of. So this is the concentration of C, and as we said, we need to know the number of moles because we put it to the power of the moles of C that we have. And then we times it by the concentration of D to the power of the moles of D that we have. So on the top of our expression, we have the concentration of the products, each of the products, to the power of the number of moles that we have of those products. And then on the bottom, we'll have the concentration of A to the power of little a, and the concentration of B to the power of little b. Okay, so I'm just going to go back to just grab this equation of the Haber process so that we can use this as an example. Excuse me. Okay, I'm just rub out all of this stuff. So if we want to show an example of how this works in practice, let's see, EG. Okay, so the Kc for this equation is going to be the concentration of NH3 squared, because we want to know how many moles there are there, divided by the concentration of N2, and then the concentration of H2 to the power of 3. So depending on the reaction equation, you could write the Kc expression for any reaction. Just a reminder as well that the reaction has to be homogeneous in order to be able to write the Kc in this way. You can write the Kc for heterogeneous reactions, but we need to only focus on the gases and solutions in that case, ignoring any solids or liquids. So I'm just going to write a little note here for homogeneous reactions. Okay. And as I said, and going back to the specification as well, so we're now looking at this bit at the bottom here, we need to be able to write expressions for equilibrium constant Kc for homogeneous reactions and calculations of the equilibrium constant from provided equilibrium concentrations. So we're not going to go into the details of the calculations at this point, although you would be able to just put concentration values directly into the expression we've written here in order to calculate the value of Kc. But that's going to be focused on more by Dr. Owusu next week, as well as how to do more complex calculations to do with that. But we also need to be able to estimate the position of equilibrium from the magnitude of Kc. So this means using the value, the number that Kc is, to estimate whether the position of equilibrium is shifted towards the right or the left. So here we've got the same kind of generic equation here described. As I said on the previous slide, if Kc equals 1, then the concentration of products equals the concentration of reactants. We just have to remember that Kc is ultimately a ratio of the concentration of products to the concentration of reactants. So if the top of this is the same, let's say this is a total of 2 moles per decimeter cubed, let's say, and then bottom is the same, then of course that's going to give us a value of 1. Okay, so that's just an example of why we can say that if Kc equals 1, the concentration of products equals the concentration of reactants. Okay, however, if the concentration of products, so this side, let's say, is greater than 1, let's say that's 10, and this is 2, then we're going to have, that's going to give us a value of 5, right? Multiple, it's less than to cube, etc. So that value is greater than 1. So looking at this bottom piece here, if Kc is greater than 1, that means the concentration of the products is greater than the concentration of the reactants. Oh, and I just realized that I spelt this wrong here. I meant to write reactants, not reactions. And then of course the opposite will be true. So if we have fewer or less concentration of products than reactants, then that will give us, what's that, 1/5, that's going to give us 0.2. So that's a value that's less than 1. So now we're looking at this one here. If Kc is less than 1, then the concentration of the products will be less than the concentration of the reactants. Okay, so again, just kind of going back to ultimately how we relate this to the position of equilibrium. If we want to talk about the relative position of equilibrium, with this first one, we would say position of equilibrium. I would say just in the middle. For the second one, if the Kc is less than 1, it means that we have fewer products than reactants. So if we look back at this up the top, we're saying we have fewer products and more reactants. And that means that the equilibrium is shifted towards the left-hand side. So we're going to say this is left. And for the opposite will be true for the other one. If Kc is greater than 1, that means we have more products compared to reactants. So that means we have more products compared to reactants, and that means that equilibrium must be shifted towards the right-hand side. Okay, so we can easily, from the value of Kc, tell whether the equilibrium is shifted towards the right, i.e. making more products, or towards the left, i.e. making more reactants. So as well as being able to write an expression for Kc, it's also important to understand what the value of Kc tells us about the position of equilibrium. Okay, so we've got a little bit of time to just do a few exam questions, just to apply what we've learned here into a more real life situation of how to apply your knowledge, perhaps to an unknown situation. Okay, so we'll look at this question first of all. So sulfur trioxide is used for the industrial manufacture of sulfuric acid. SO3, sulfur trioxide, is produced by reacting sulfur dioxide and oxygen as shown in the equation. So we've got that equation. Forward reaction is exothermic based on the delta H we've been given. The Chatelier's principle can be used to predict how different conditions affect equilibrium position. Using Le Chatelier's principle, show that a low temperature and a high pressure should be used to obtain maximum equilibrium yield of SO3. Okay, and explain why the actual conditions used in industry may be different from the conditions needed for a maximum equilibrium yield. So this is what we were talking about on the slide about industrial conditions and a compromise between yield and rate. So first of all, we want to show that a low temperature and a high pressure would be used to obtain a maximum yield. So in this case, a low temperature, because the forward reaction is exothermic, and this equilibrium would be shifted to the right, or in the direction of the products, maximizing the yield. High pressure, because we have 3 moles of gas on the left and 2 moles of gas on the right. 3 moles of gas on the left-hand side, and 2 moles of gas on the right-hand side. Therefore, high pressure will shift the equilibrium to the right-hand side, which is in favour of the forward reaction and producing more products or increasing the yield. Then explain why actual conditions used in industry may be different from the conditions needed for maximum yield. And then you would talk about considerations of rate, perhaps safety, because it may be dangerous to maintain a very high pressure, and economics, i.e. cost of the reaction. So perhaps we might want to have a higher temperature and a higher pressure for the rate consideration, but we wouldn't want to have too high of a cost. So we want to be able to balance all these different things. And we'll just flick to the mark scheme to just check what it talks about there. So again, it says 4 marking points. You've got forward reaction is exothermic because the delta H was negative, and then right-hand side has fewer gas moles for the pressure side of it. Therefore, we've got the correct equilibrium shift in terms of pressure, i.e. shifting towards the right, and the correct equilibrium shift in terms of pressure, i.e. shifting towards the right also. Industrial conditions, we talked about the low temperature would give a slow rate or a slower reaction, or we might use a high temperature to increase the rate. And then we talked about the potential of a safety risk, or that it might be too expensive to use a lot of energy. So again, referring back to those main points of yield, rate, safety, and economics when we're talking about factors in industrial conditions. Okay, now I'll go on to the next question, which was related to this first one. So, under certain conditions, Kc for equilibrium, for that equilibrium is 0.16 decimeters cubed per mole. The equilibrium mixture under these conditions has the following concentrations of SO2 and O2. So that's our reactants. So these are equilibrium concentrations of SO2 and O2. Using the value of Kc, explain whether the equilibrium position will be towards the right or towards the left under these conditions. Okay, so this is where we need to think about, is it greater than 1 or less than 1? So 0.160 is small or is less than 1, which means, as we said, if it's less than 1, that means that the products on top must have been less than the reactants on top. And that means that if the products are less than the reactants, then we've got the equilibrium shifted towards the left. This means the position of equilibrium, or the equilibrium position, is towards the left hand side. So whether the equilibrium position will be towards the right or the left, we said it's towards the left because 0.16 suggests that we have a smaller concentration of products compared to reactants, and that therefore we've got lots of reactants compared to products. That means that our equilibrium is shifted towards the left. So if you need to, it might help to actually write the expression of Kc in this case, but you don't have to answer that part of the question. And then it says to calculate the concentration of SO3 in the equilibrium mixture. As I said before, we weren't going to concentrate too much on calculating concentrations in this case. However, since we've been given a value for Kc and we've been given the other equilibrium concentrations, you could quite easily do this without too much extra knowledge. Just write the expression for your Kc. So equals SO3 squared divided by SO2 squared and O2. And then you just need to rearrange this equation to make SO3 the subject. So we'll rearrange it to make SO3 the subject. And that's going to give us Kc times SO2 cubed and O2, sorry, not cubed, squared, and O2. Okay, and of course, if you actually want to just find the concentration of SO2, SO3, we can just do a square root there and do that all in one. Just not. Okay, so we've got the value of Kc is 0.16, and we have SO2 is 2.0. So we square that, and then we've got 1.2. So type that all into a calculator, and that should give you your concentration for SO3. I'll just do that quickly now, just to check that I get the right answer. But 0.160 times by 2 squared times by 1.2, and then square root that. That gives me 0.87635, blah, blah, blah. So 0.876, and we'll just double check that answer. Yeah, so that's the answer. Again, just looking at the mark scheme, the value of Kc, Kc is small or Kc is less than 1, and the equilibrium position is towards the left, and then your calculation giving you 0.876. So as I said, in the next lesson, Dr. Owusu is going to focus in a lot more detail on calculations involving Kc. So how to calculate the value of Kc, not just from concentrations given to you or from the equilibrium concentrations, but also from more realistic information that you would get, like such as how much of something you put in at the beginning, that's your initial concentration, and how to work out your equilibrium concentrations from that, as well as calculating the units for Kc correctly. And he'll also look at Kp as well. So that's it for today's session. As I said, in the next session on Sunday at 1 p.m, Dr. Owusu will be going through in more detail how to do calculations for Kc as well as the units for Kc. And he'll also look at Kp, the equilibrium constant for gases, in more detail. So if you do have any questions about today's session or any of the other sessions we've had so far, then do email us at chemistry@boostrevision.com, and we'll be happy to answer your questions as soon as we can. Thank you very much for joining us today. Do keep an eye out on the website and for your emails for reminders about the sessions that are coming up soon. We did originally have a schedule for Year 12 that was going to help to support you towards your Year 12 exams, but obviously since that's all been changed, we will be changing a lot of the workshops coming up over the next few months. So Year 12, rather than preparing for end of year exams or AS exams, we are going to be starting to teach you more of the A2 level content. So next lesson, for example, Dr. Owusu's session is kind of building on to what I did today, which was the AS equilibrium content, and giving you more of the A2 equilibrium content that you'll need to sort of bridge the gap between this year and next year. So hopefully these the next sessions that we'll have over the next few months will help to support you in this time that you're off school and doing a lot of this learning yourself. Do join live if you can, so that you can ask any questions that you may have to clarify things and check your understanding. But otherwise the replays will be available from 48 hours after the time of the session, and feel free to ask us questions in the comments on the website, or as I said, by email anytime. So thank you again for joining. Do join Dr. Owusu on Sunday, and keep up to date with us for sessions, more sessions coming up. Follow us on Instagram at BoostRevision, and hope you have a good week and weekend. Until then, stay safe, stay home, wash your hands, all of that kind of stuff. Be safe and healthy. I hope your families are all doing well, and see you again next time.